Today we're going to take a look at factoring binomials. So binomials are two terms. So factoring them, now remember when we are multiplying two binomials together, a couple things can happen. But in this form, we're looking at a factoring the difference of two squares. So that would look like this. That would look like if we were multiplying something like x minus 6 times x plus 6. So think back to what happens when we multiply two binomials that look like this, x minus 6 times x plus 6. When you go through the multiplication process, the middle terms just end up canceling out. So since those middle terms end up canceling out and we're left with minus whatever that multiplication is, minus 36 in this case, this is called factoring the difference of two squares, x squared minus 36, where x squared is a perfect square because x times x, and 36 is a perfect square because 6 times 6, and it is a difference of two squares because there's subtraction. So when we have this scenario of a difference of two squares, so let's say a squared minus b squared, we can just factor this to a minus b times a plus b. Just like how I was showing you here, x squared minus 36 was the result of multiplying x minus 6 times x plus 6. Not x minus 6 times x minus 6, where we have that same term squared, that same binomial being squared. It's not like that. It's the difference of two squares which results in this plus and minus. So when we have a squared minus b squared, we can just factor it to a minus b times a plus b. So number one, x squared minus 25, x squared is x times x. So this is x, this is x. 25 is 5 times 5, and it is a double check. Make sure it's a difference of two squares. So that's going to be x minus 5 and x plus 5. And the order of the minus 5, plus 5, plus 5, minus 5 doesn't matter. So it's the same thing. And then number two, 36x squared minus 1. 36 is a perfect square. X squared is a perfect square. That's going to be 6x, because 6 times 6 is 36, x times x is x squared, and then 1 is 1 times 1. So the difference of two squares, because 36x squared is a perfect square, 1 is a perfect square, so I'm going to rewrite this as 6x minus 1 times 6x plus 1. Number three, x squared y squared minus 100. X squared y squared is a perfect square because xy times xy would get us x squared y squared. So even though there's multiple terms that are squared, it's still a perfect square because xy times xy gets you right back to x squared y squared. So this is going to be xy, and then 100 is 10 times 10. So xy minus 10 times xy plus 10. So xy minus 10 times xy plus 10. Difference of two squares. Two squares means a difference. Subtraction. Subtraction means difference. Now 4, we have negative 144x squared plus 1. So you might be thinking, well, I can't really do anything because that's a perfect square. That's a perfect square. 1 times 1. 1 is a perfect square. But this is a sum of two squares. That's not a difference of two squares. Correct. Can't do anything in the current form, but what we can do is factor out this negative. You can take out that negative, or you could actually technically, you can rewrite this as 1 minus 144x squared. That's actually potential, but I'm just going to go with factoring out the leading negative. So I'm going to take out the leading negative. So that's going to leave me with positive 144x squared. And then this, since I'm taking out the leading negative, plus 1 is going to become minus 1. So now I do have a difference of two squares. I have 144x squared is a perfect square because 12 times 12 is 144. X times x is x squared. And then 1 times 1 is 1. So I do have a difference of two squares. I just have to make sure I tag along that negative. So now it becomes 12x minus 1 and 12x plus 1. Where here, if you did it like this, you get the just same answers, but flipped around. So it would be 1 minus 12x and 1 plus 12x. So interesting problem there. That's a cool problem. Interesting how that worked out. All right, number 5, 25x squared minus 49. So 25 is a perfect square, 49 is a perfect square, x squared is a perfect square. So this is going to be 5x minus 7 times 5x plus 7. And I can't emphasize this enough. This also you could write this as 5x plus 7 times 5x minus 7. Like, it doesn't have to be the minus first and the plus. Like, it doesn't really matter because it's all the same. But just as long as you have a minus and a plus. So you got to make sure this is a subtraction difference of two squares. Let's go to the next page. So this one's kind of, you got to think a little bit. Kind of interesting. You got to think. Factoring x to the fourth minus y to the 10th. So look for a difference of two squares, because we have a binomial. So look for a difference of two squares, x to the fourth and y to the 10th. Think about what squared would get me x to the fourth. So x to what power, x to what power squared would get me back to x to the fourth? Well, what operation do I perform with this exponent here and this exponent? I multiply. So this would have to be x to the second to give me x to the fourth. Take that same logic. Can I apply that to y to the 10th? So something to the second, so y to some power to the second to get me back y to the 10th. Again, what operation? Multiplication. So 2 times what would get us y to the 10th? 2 times 5. So this would be y to the 5th to the second. So now this is actually a difference of two squares because I'm able to rewrite this as perfect squares. So this is x squared squared minus y to the 5th squared. This is a difference of two squares. Just like how I was talking about like x squared minus 25. This is x to the first squared minus this is 5 to the second, or 5 squared. So I took x minus 5 times x plus 5. So I took that term that was being squared. Same concept here where x squared is being squared. So this is going to be x squared minus y to the 5th is being squared. So x squared minus y to the 5th. And x squared plus y to the 5th. So not impossible. A little bit of a tricky scenario there to look through and make sure you catch that you can actually rewrite those as perfect squares. Number 7, 9x to the third minus 49x. So look for a GCF. 9 and 49, I can't take anything out. But the x's I can, because I have x to the third and x to the first. So I'm going to take out x to the first. That's going to leave me with 9x squared minus 49. I took out the x. So just like how I've been saying with taking out GCF, make sure you tag along that GCF for the ride. That doesn't just disappear. So since I took out the x, now I have a difference of two squares. Because 9 is 3 times 3, x squared is x times x, and 49 is 7 times 7. So x times, I just wrote 9x, but it's 3x. 3x minus 7 times 3x plus 7. So difference of two squares. So that was the difference of two squares. Now let's look at the sum or difference of two cubes. So we have a to the third plus b to the third, or a to the third minus b to the third. When we have a to the third plus b to the third, what we're going to do is use this formula, and that's going to be a plus b times a squared minus ab plus b squared. So a plus b times a squared minus ab plus b squared. But if we have a difference of two cubes, it's going to be a minus b and then a squared plus ab plus b squared. So just if you want to try to commit this to memory, the letters don't change. It's ab, a squared, ab, b squared. The thing that does change is the signs. So when it's the sum of two cubes, it's plus, plus, minus. So if it's a sum, the first one's the plus, and then we have the minus. If it's a difference of two cubes, the first one's the minus, the next one's the plus. So whatever it is, the sum or difference, that first one's going to be that same sign, and then you take the opposites for the next one. And then this is always going to be plus b squared for that one. Not needed to commit to memory, though. So you just write it down, know the formula, where it's at, how to use it. But if you want to try to commit that to memory, the letters do not change. It's a squared, b squared, but then the signs do change. Let's take a look at a couple problems. Let's have a couple of these factoring the sum or difference of two cubes. X to the third plus 27. So think about what is being cubed in both scenarios. So here the x is being cubed because x to the third, and then 3 is being cubed. That is a sum of two cubes. So I'm going to have x plus 3 times x squared minus 3x plus 3 squared is 9. So this was 3 squared because my b term was 3. My a term was x, so b squared is going to be 3 squared, so that's 9. Number 9. Factor y to the third minus 8. This is a difference of two cubes because y is being cubed and 2 is being cubed. 2 to the third is 8. So now I'm using the difference of two squares. So that's going to be y minus 2 times y squared plus a times b. So that's going to be 2y plus b squared is 2 squared. So that's 4. Last one, 64x to the third minus 1. Not the easiest one to just, like, oh, it's that. So if you have to think about this a little bit and maybe play around with your calculator a little bit and check what is the cube root of 64 if you don't know it, that's 4. So then, oh, 64 is a perfect cube. X to the third is a perfect cube. 1 is a perfect cube because 1 to any power is 1, so you can make it 1 whatever you want. It's a perfect square, it's a perfect cube, it's perfect everything. So this is going to be 4x to the third minus 1 to the third. So a difference of two cubes. So that's going to be, let's look at our formula, a minus b. So 4x minus 1. And then it is your a squared. So be careful here. A squared is going to be 4x squared. So that's 16x squared because 4 has to be squared because 4x times 4x. So 16x squared and then plus 4x times 1 is 4x plus 1 times 1 is 1. The sum or difference of two cubes doesn't appear a whole lot. It does appear though. It's something that you need to know, something you need to be used to doing. But the problem with it is that I've always had with it is like I'll get it to memory, I'll commit it to memory, and then like I won't see it for 2 weeks in a problem, and then it'll pop up and be like, oh, I don't trust myself in knowing if it's at minus plus or plus minus or what's the order of the signs. So I always have to go back and double check whenever I'm like doing some problems. But if you just keep practicing it common, it will stick to your memory. But it's not something that happens a ton, but it is really useful to know in those times where it does pop up. So this was factoring binomials.